Dear audience, we will now have the special forum number 2, the zero emission buildings. This session is a combined session of the Nordic Passive House Conference and Sustainable Building 11. And for our first speaker, I'd like to ask Janne Jormalainen telling us about implementing zero energy buildings in Nordic climate conditions. Please, Janne.
Thank you, Riikka, and good afternoon, everybody, also on my behalf. So as said, I'm Janne Jormalainen. I'm representing a company called SPU Limited. We provide low, passive and zero energy structural solutions in the Northern European market. I'm a chairman of the board at SPU. And before I actually start my presentation, I wanted to start by asking you a question. So since we are talking about energy efficient buildings and sustainability, let's have a show of hands. How many of you are living in a passive or zero energy building today? I think if I calculated right, it was 3 plus myself, if I'm not wrong. So there are few people living in very energy efficient buildings as well. So the reason for asking that question was actually that I have myself lived 2 years and 4 months now in a passive house here in Helsinki, and I have to say that yes, the energy bill is very low, but the real thing, what my wife always wants to say, is that the indoor environment is wonderful. So I believe that we are really by building energy efficient buildings, we are doing good not only for the environment but also for the living conditions of people. And I think that we are on the right track to do so also in the future. Okay, but I will present shortly a case study, an example of implementing a near zero energy building in a Finnish climate conditions. And here you will actually see 3 examples of such buildings that have been recently implemented here in Finland. All of them are described in my paper, which in the full paper, but I will now concentrate for the sake of time on the Kuopas building, which you will see here on this picture on the upper left-hand corner. So that building is such that it's an apartment block building, and it's an apartment. It's apartments for students. It's a reasonably large building to be a, if you like, a pilot building, but in any case, and the cost of implementing this, the building cost of this building was 2,700 euros per square meter, about 10% above what we would typically have in Finland in a building which fulfills the current building code. So that's what the building is like. I will just briefly talk about the structural solutions used here. It's a very typical Finnish apartment block building. So concrete sandwich element walls, hollow slab roof, and you know, in principle very similar to what all, or not all, but many apartment block buildings in Finland today are. The difference here is that the building envelope is extremely has extremely low U values. So the roof has 0.07 and the walls 0.08. And the air tightness of this building was measured to be less than 0.4 times per hour. So typical structures, insulation material here used is polyurethane to keep the structures reasonably thin, and also to achieve good hydrothermal performance of the structures. There you see a couple of pictures from the building side when the elements were installed. So typical sandwich elements as you see there on the left-hand side picture. So what makes, of course, this now the zero energy building is the fact that then it's also including the energy production. So the energy consumption firstly is consisting of these elements, and as you can see, this is not now, these calculations are not including the electricity that the tenants use in this building. So this is a rental apartment building. But everything else is included, also including the domestic hot water. So ventilation taking about 1/3 of the energy consumption, and the rest then you see there on that picture. The space heating demand of this building is 10.6 kilowatt hours per square meter per year. Now, how does the building then produce energy is here. So it has a little bit over 100 square meters of photovoltaic panels and 125 square meters of water heating solar panels. In addition to that, it's using also geothermal energy wells, and you did hear that right, so it's not using heat pumps, it's using energy wells to actually preheat the incoming air during the winter time, and then cooling the air during the summertime. And the building is connected to both electricity grid and the district heating grid as well. So it has the possibility of also giving energy back to the grids, as we see on this picture, which is the energy balance. So during the summer months, there's excess energy that is produced, and then during the winter months, it's the other way around. The total energy balance of this building is a little bit over minus a little bit less than 2.3 thousand kilowatt hours per year, and basically this building was implemented in an environment where the annual average temperature is less than 3 degrees. So it's reasonably harsh environment, if you like, for building a zero energy building. Costs, which we all are of course concerned about, is in these pilot buildings was about 10% more than in a typical building of similar for similar purpose implemented in Finland, and mainly this is due to the technical systems, i.e. the energy production on site. And what I would suggest from the study of these buildings and a number of other buildings is that the most of the cost when we implement zero energy buildings today goes into the energy production, implementing the energy production on site. So I think some of the considerations we should put into is producing renewable energy for building groups or smaller areas, if you like, and also for the fact that the energy production could also be introduced in a later stage for these buildings, i.e. make the building envelope capable to support zero energy building, but if there is a lack of financial resources in the building phase, implement the technical systems to produce electricity and other energy in a later stage. So that would be my conclusion from here. But as said, these buildings were implemented over the last 2 years in Finland, and hope that then we will have more experience also from the actual users of these buildings to tell in the next conference. Thank you.
Thank you very much. Are there any questions from the audience? We don't have any questions now on the message board. Yes, please.
Could you just clarify, you were saying that you're dealing with the fabric of the building first, so that you have passive control before you add the machinery that then modifies your environment. So could you just describe the fabric, the same as the walls, that they appear to be concrete, sandwiching, insulation, and they're prefabricated, is that right?
Yes, that's correct. So the question, I'll just repeat the question. So the question was that how is the building envelope done? So yes, the building envelope in this case was concrete sandwich elements with polyurethane insulation inside. Was that your full question?
But that you're using the fabric first and foremost to provide, say, thermal mass to help reduce the energy that you would need from systems that you're installing first. That's the first principle. Is that correct?
Well, the thermal mass, of course, is there to help as well, as we all know. But this was my conclusion, if you like, at the end was more to the fact that it costs a minimal amount to make the building envelope zero energy, capable, if you like. But the building envelope is going to be there for the next 50, 100 years. We will have huge development in technical systems to provide actually energy on site during that development time. So what I'm suggesting is that perhaps to consider building the building envelope so that it's capable of supporting zero energy buildings when there's more development in these other technical systems.
Thank you. Yes, please.
Sorry, I don't know whether this is on. Just a question about the standard of the envelope. Was this to Passive House standard or to a standard that you've developed as a company?
So this is a little bit more than Passive House standard. So typically today in Finland we would implement the Passive House with U values, for example, in a wall which would be 0.09. So this had 0.08, so a little bit less. And this is only to reduce the amount of heating energy needed throughout the year. So this is a little bit more. And I'm now talking about the Finnish Passive House standard, which is done by VTT, so not the German one.
Okay, thank you.
Thank you.
Thank you very much. Our next, yes. Our next presentation comes from Norway. Mr. Finocchiaro is telling about the building form, climate and energy supply system in a passive house building. Please.
Thank you. Good afternoon, everyone. I'm here presenting this work in spite of my colleague, Mattias Aase, that could not be here today presenting because of some problems in Trondheim. But I'm going to give you an overview about the project that is today under development in our department of Architectural Design, History and Technology, together with the support of the ZEB Center on Zero Emission Buildings and SINTEF. So the project that I'm going to present to you is a project that is today under development in a total integration with the students, so the academic courses and the students are working pretty hard to develop together with us. So it's a sort of international competition whose aim is somehow enhancing the connection between researchers, academics, private companies. Okay? So a little bit an overview about the content, what we are saying, and I go straight into the introduction. The Solar Decathlon competition, that's how it's called. It's an international competition that involves 20 universities that are coming from all around the world, and is going to be held next year in Madrid, in next September exactly. And the aim of this competition is that one of developing a prototype that is energy positive, thanks to the integration of different photovoltaics, but also has satisfied a whole bunch of different requirements. So it's oh, I'm sorry, there is an image is missing. Oh, here's there. Okay. So in the solar decathlon, the students compete to produce a highly efficient, completely solar-powered house, able to generate enough electricity for all kind of domestic activities that would be normal in any kind of house. So if you can see, providing thermal comfort condition, sufficient lighting requirements, but also the students, when we'll be there next year, they will have to wash clothes, invite people for dinner, and do all series of things that like it's a real normal house. The house will be evaluated under 10 different contests. So the energy balance that I'm going today to speak about, it's just one of the different requirements under which the house will be evaluated, and it's exactly here. So in the energy balance and solar systems, but the jury will also evaluate different aspects like the architecture, the aesthetics of the house, but also the communication and the social awareness. So how the project was used to increase the social awareness about the use of photovoltaic technologies, and then the strategy used in the competition. Just one word. So as you could imagine, the house that we were asked to develop should have been market ready for our country, so a Scandinavian house somehow, but should have been able to perform optimally in Madrid. So it means a completely different climatic context. And what we teach to our students in our Master of Sustainable Architecture is to understand how the design of a house should be related to the climatic context. So you could understand that there is a huge contradiction behind that of requiring a Scandinavian house to perform well in Spain. So obviously the focus on flexibility and climate adaptability of our project was something that was central in the entire process of development of the house. We started designing the house looking at the passive house standard requirements, and we started as a first step to look at specifically Madrid and try to understand how the house could have performed according to passive house standards in that context. And here are the requirements that we had. So like, as you know, 15 kilowatt hours per square meters of heating demand and cooling demand, and then a total demand of energy of 120. And the main challenge, as I told you, was that after coming back to Madrid, so coming back from Madrid to Trondheim, the house will be used actually next year as a research living lab from ZEB by the Zero Emission Building Center. So obviously the adaptation strategy for allowing an optimized performance was crucial. And the other difficulty were coming from the requirements of the competition, like the fact that we were dealing with a really narrow comfort zone, that we are asked to be able to have a house that is able to maintain comfortable condition, but exactly between 23 and 25 degrees centigrade, and also relative humidity between 40 and 55. So if we want to score points next year when we compete with other universities, we have to be inside this range of values. So the challenge was pretty high. The methodology that we used in the architectural design was that one of designing somehow a building that was characterized by different layers of, so the envelope was a multi-layer envelope that could have been working in different ways according to different seasons. So okay, then obviously when we performed the calculations, the calculations have somehow satisfied the passive house requirements in Madrid, but they didn't satisfy the passive house requirements in Norway. So we started applying an adaptation strategy following the Kyoto pyramid. So the first to look at that, reduce heat losses through the windows, then maximize the solar heat gains, and then reduce the transmission losses through the walls, floor window, roof window. What does that mean? It means basically that Matthias defined 4 different models of 4 different groups of parameters that I'm going to run and then go back. So these ones. So this one was the parameters used for the simulations in Madrid, and then 4 different groups of new parameters for the Norwegian context with more and more stringent envelopes. It means like the U value was going down, down, and down, down until this is the mean U value, 0.22. If you want to more have more detailed values, you can refer to these tables that you can find. But basically, we have, for the Madrid building, U value of 0.25 watt per square meters Kelvin. And then air tightness was down to 0.07, and so on. Okay, so I just spent a couple of words about the concept. As I told you, the main idea was that one of having somehow a really regular box. Now the project is slightly changed, but this one was the original idea. That was characterized by a high mobility of all the external envelope. We had 3 different layers of devices, and all of them were movable. The first one was characterized by shading device and also movable insulation, and the most internal layer was also able to translate in this direction. In this way, we were trying to solve the contradiction of having a passive house, Scandinavian house perform that was asked to require Madrid. Basically, we were somehow canceling this one when we wanted to have a greenhouse here, or moving this one here when we want to have a double skin facades, etc. But obviously this was constructively really complicated, so now we are moving to another kind of stage. If you want to know more about this project, please ask us. I don't want, I think, to take too much time now to refer all of it. A little bit about the results. Okay, so as I told you, these are the 4 group of parameters, and this is a little bit the result. So on top of the 0, you can see the energy demand of the building in oil and electricity, and below the energy production that would come from the photovoltaics. The energy production obviously is changing from context to context. It's pretty obvious that in Madrid we have a pretty big energy production thanks to the high solar radiation, and much smaller in Oslo, that was assumed as a reference climate for a Norwegian context. But anyway, the prototype showed that it's possible to have energy positive buildings also in this climate. I will just mention that the maximum power of the photovoltaic systems that were applied is something that it's coming from the competition requirements. So we have a 10 kilowatt power maximum all around the year. And then let's go on. So if we try to summarize then these results into a final diagram, then we'll have, this is what happened. 120 is the limit that we had for passive house requirements. This one is the Madrid building. And as you can see, here we have the energy supply coming from the PV, and here the energy demand. So we are still always inside the 120, and we have a pretty high production thanks to the PV integration. So it's supposed, this line that you can see here in 45 degrees, it's the net zero energy. So basically it's when the demand is balancing the energy production. So all the 5 buildings that Matthias analyzed here, so 1, 2, 3, 4, 5, are somehow, are somehow over the line. But there is one that it's the first case where the envelope of the building was not yet that much stringent, so that it's not yet satisfying passive house requirements, that is this one. All the other 3 that were simulated are passive house requirements, but obviously the result for the Norwegian context is that the most stringent one, so the one with low U value, is the most efficient one. So, I don't know if I'm running too much. Didn't calculate, no, it's okay. So a little bit about the conclusions. The energy calculations that here were done focused somehow on 2 systems. One is the envelope system, so the characteristics of the envelope and the U values, so the degree of insulation, and the one other is the energy supply system. This one formed somehow, it's, as I told you, these were the preliminary set of analyses that were done with the original concept. Then now we are in the 4th stage of development of the project, so there are now new set of analyses that have been done also with other software. And the results show that actually it's the challenge that were coming from designing somehow as a house that performed both the contest in satisfying passive house requirements in both of them. How much that would have been difficult, but what I will stress a little bit more is that the these final two lines that are really interesting for us also according to what the Solar Decathlon competition asks us to promote. So it's just like that the results indicate that solar applications integrated with other energy supply technologies should be further developed for the Norwegian market until they provide cost-effective solutions. So what we are trying to show in our project is that actually there is a marginal applicability of these photovoltaic systems even in cold climatic contexts or where the solar angle is so low, so that if we respect somehow passive house requirements for the energy demand, we can still have an energy balance all along the year. There are some discussion behind that, also with the provider of the PV panels, but we're working hard. And this one would represent a helpful somehow result for the development of passive houses and net zero energy house in our context. Okay, I don't know if okay, thank you. That's all.
Thank you very much. And now we have time for questions, please. Yes.
Sorry. That's really interesting. It looks like the graphs show it's... Yeah, thank you. Thank you. Can you all hear me? Thank you.
Yeah.
That was a very interesting presentation, and it seems to me that the building in Madrid is much more challenging than the building in Norway, Trondheim. Presumably, you've got active cooling specified.
Yeah.
Could you just say something about the cooling systems? Because it's important to know how it's cooled in Madrid and how it's kept warm in Norway, and whether it's the same system.
Yeah, obviously, as you said perfectly, I mean, the requirements, they are completely different due to climatic context. So obviously in Madrid, we have much more stress in the cooling and shading devices. On the other hand, in the Oslo climate, we have much more stress in limiting the thermal losses through the envelope. Okay, so that's a completely different approach. But the point is that for Madrid, we have now a really slightly different strategy for solving this contradiction now to compared to what we presented now. But the focus on Madrid is that one of having an hybrid system. So basically the thermal comfort zone is so small that it's not really easy to predict if the external condition, even if we are in September, will be inside that specific parameters, okay? Inside that range of. So the point is like we are now stressing the possibility of having, anyway, also in Madrid, a really stringent envelope, a really insulated envelope, but having the possibility of naturally ventilating the house. But since we don't know if we are inside that range, in combination with some sensors, the house is somehow the air, or the external air, is either accessing straight inside the house through a cross ventilation systems, either going inside a compact unit that is also working like it's a compact unit for both heating and cooling systems, and their air exchanges is there, and then getting in. But the main idea now, this is, as you can say, I mean, we're stressing about the possibility of, because this sort of kind of approach would have presumed that when we move from Madrid to Trondheim, then we have to change the components and the envelope. On the other hand, what we are trying now to stress is that we can still use the same component, just have an advanced system that is able to somehow tell us when the valves should be open and let the air in or close, so having completely different behaviors anyway, using always the same envelope.
Thank you very much.
Thank you.
Our third presenter comes from Sweden, and the title of her presentation is Towards Zero Energy Office Buildings in Northern Europe. Please, Kaisa Flodberg.
Good afternoon, everyone. During this presentation, I will give you the method and results from daylight simulations carried out in a single office room in a Nordic country. My name is Kaisa Flodberg, and I'm a PhD student at Lund University. But just as a previous speaker, I'm here on behalf of my colleague, Marie-Claude Dubois. She is the one that carried out the simulations. Marie-Claude is an architect and researcher at Lund University and the Division of Energy and Building Design. Marie-Claude and I, we work together in a Swedish research project called Energy Efficient Office Building with Low Internal Heat Gains, Simulations and Design Guidelines. And the overall purpose of this project is to provide knowledge to the Swedish building industry on how to design cost-efficient office buildings with a good indoor climate and very low energy use. And we believe that this is a first and important step for developing future zero-emission and zero-energy office buildings. And the project is financed by the Swedish building industry and the Swedish Energy Agency and a large construction company in Sweden called NCC. And the objective of this simulation study is to investigate the daylight potential in single office rooms in the Nordic countries, that is, countries at high latitudes. And we want to see the potential for electricity saving for light. And the goal is to provide guidelines for architects and engineers. So in this parametric study and simulation, we use the simulation tool DaySim. And in DaySim, we can change the following parameters: the glazing to wall ratio, different climate files, the orientation of the room, the reflectance of the inner surfaces, the visible transmittance of the glazing, different shading device, and the electric lighting strategies. And the ones with a black color, I will give you the results from these studies today. So first, we modeled a base case in DaySim. And this is a single office room in Stockholm, facing south. And in the base case, the amount of glazing on the wall is 30%. And the visual transmittance is 72%. And the reflectance of ceiling, walls, and floor are 80, 70, and 40%. And we assume that the office room is occupied from 8 to 5 every weekday. And on this picture, you can see the different illuminance sensors that we placed in the room. And this distance from the window, 1.5 meters from the window, is the preferred sitting zone. And in this study, we analyzed the daylight autonomy continuous, which is a factor of how much available daylight you have in a room compared to the required illuminance in the room. So for instance, if we want 500 lux in the room and we have 400 lux from the daylight, then the daylight autonomy is 80% for this time step. And we also studied the daylight autonomy max, which is the percentage of time during a year when we have too much daylight in a room, which is a risk of glare. And we should keep this below 5%. And we also studied the electricity use for lighting systems. I will now try to guide you through Marie-Claude's results, some of the results. Here you see the effect of the daylight autonomy as a function of glazing to wall ratio and at this different distance from the window. And I want you to concentrate on this gray curve. As you can see, the daylight autonomy increases sharply from 10 to 30% and then stabilizes. And at 30% glazing to wall ratio, we have 78% daylight autonomy, which is at the borderline between good and excellent. And if we look at the glare risk down here, remember the 5%, we want to have, don't want to have glare risk more than 5% of the year. And above, if you have more glazing than 20% of the wall for this preferred sitting zone 1.5 meters from the window, so above 20% window glazing to wall ratio, then we will have a glare risk and we will need to have shading devices. We also investigated the effect of climate in relation to glazing to wall ratio again. And in this study, we included Montreal and Quebec, which are cities at a lower latitude than the Swedish cities, Stockholm, Gothenburg, Malmö, and Östersund. And in Quebec and Montreal, we have more daylight benefit in the room. It is actually excellent. But we have good daylight in the Swedish cities as well. The differences between Gothenburg, Stockholm, and Malmö are negligible, but in Östersund, which is further north of Stockholm, we have a little bit more limited daylight, but still quite good. And this graph shows the effect of orientation of the room. And as expected, we have more daylight in the south orientation and less in the north orientation, and we have the same daylight amount in the west and east direction. And if we look at the glare risk, and remember again the 5% limit, at the south facade, we have a glare risk already at 20% glazing to wall ratio, but at the west and east facade, it's at 30%, and at the north facade, we can manage without shading devices. This graph shows the effect of electric lighting systems. And we have the electricity use for lightings in the room, and we have the glazing to wall ratio again. And this curve with the triangles, it represents the standard manual switch near the door. And as you can see, the occupancy sensor actually consumes more energy than the manual switch. And this is because the occupancy sensor turns the light on every time you enter the room. So between 8 o'clock and 5 o'clock every day, the lights are turned on, even though we have enough daylight in the room. So instead of the occupancy switch on and off systems, we should have an occupancy switch off system, which turns the light off when we walk out of the room, and then when we enter the room again, we have to manually switch the lights on. So if we have enough daylight, we won't switch on the lighting, and then we will save energy. And the best control strategy is to combine this occupancy switch off with a photoelectric dimming system, which will adjust the lighting. If we have much daylight in a room, we can dim and adjust the lighting electricity. And I will end this presentation with some main conclusions from this study. The optimal glazing to wall ratio in terms of daylight autonomy for single office room in Sweden is between 20 and 40%. And the continuous daylight autonomy increases sharply with glazing to wall ratios increasing from 0 to 30%, but stabilizes afterwards. And the benefits in terms of daylighting of increasing the glazing amount from 40 to 60% are marginal, and they are non-existent for an increase from 60 to 80%. And at the south orientation, for a south orientation, a 20% glazing to wall ratio provides good daylight without major glare risks. And one design advice is to seek for glazing to wall ratios of 20% for the south facade, 30% for the east and west facades, and 40% for the north facade. And daylight autonomy is more limited in the Swedish cities compared to cities at lower latitudes like Montreal and Quebec. But it is still possible to achieve good to excellent daylight design with reasonable glazing to wall ratios in Sweden. And there are negligible differences in daylight autonomy between the three largest Swedish cities. and Östersund has a slightly more limited but not significantly lower daylight autonomy than Stockholm, Malmö and Göteborg. And for the electric saving, automatic switch on and off system yields more energy use than an ordinary manual switch near the door, and photoelectric dimming with occupancy switch off allows reducing electricity by at least 50% compared to a manual switch near the door. And a more detailed journal article will be presented in the next number of Lighting Research and Technology. And if you have questions about this and you want to know more detailed results from this study, please don't hesitate and contact Marie-Claude Dubois, this email address. Thank you.
Thank you very much. Are there questions from the audience? Yes, please.
It's Richard Hyde. I'd just like to see whether you've managed to optimize the relationship between the daylighting and the heat losses or heat gains through the windows.
Yes, that's what we're doing right now. In this study, we did not at all focus on thermal simulations, but we have done simulations in Ida ice afterwards, and we can see that the larger glazing to wall ratio, if we increase the glazing to wall ratio, we also need more heating and more cooling energy for the whole year.
Okay. Thank you, and there's a question also here in the front row.
Thank you. Two things. You're probably already familiar with this, but have you come across the LT method that was developed at Cambridge University in the UK? They did very similar things to what you're doing with a series of curves, the LT curves, lighting and thermal curves, that dealt with the proportion of a facade that's glazed from sort of 0 up to 90 or whatever, and it's very similar stuff, but done quite a few years ago with an older technology of building fabric. I don't know if you're aware of that work, but it's worth looking at.
I'm not aware, but I think I'm pretty sure Marie-Claude is aware of that, because she has, well, she knows that this is in the same, well, it shows pretty much the same thing.
Okay, I mean,
but for the Nordic
various
climate.
things may have changed in the context of energy and lighting technology since then. I just thought it might be useful for you. What interests me was this concept of daylight autonomy, rather than what perhaps we in the UK would always describe as daylight factors in a very crude sort of 2%, 5%, 10%. The question I wanted to ask was how, in terms of daylight autonomy and glare risk, you have these limits between good and excellent at 80% and another one at 5% if the risk is high. Are those percentages something that form part of the Swedish regulations,
no.
Or are these figures, how did you decide that 80% was the point at which you went from good to excellent?
These are results from a literature review Marie-Claude performed last year, and she found these limits in different studies and literature. So they are all presented in the full paper, in the references.
Okay, thank you very much. And the next presentations come from Egypt. Mr. Nadim will tell about how to achieve zero carbon emission in the UK construction industry, integrating off-site construction and renewable energy technologies. Sorry, Mrs.
Good afternoon. Today we have looked at different technologies that can be used in the buildings and the built environment in general. Our presentation today will be looking at a more holistic view of the challenges of meeting the zero carbon emission in the UK by integrating it with the off-site construction technologies. Oh, sorry. So the greenhouse gas effect has resulted into the increase of the global temperature all over the world. And if we continue like this, this will cause serious implications on Earth. So this will threaten the life on Earth. And the major gas contributing to the greenhouse effect, as we all know, is the CO2, carbon dioxide, and is resulting from the burning of fossil fuel to generate energy for the different buildings. And as we can see here, that domestic is the major domestic buildings are contributing to the to the carbon emission in the UK. This is because of the use of the burning of fuel to generate electricity resulted into buildings becoming energy inefficient because of the mass exploitation of fossil fuels. In the built environment, 50% of the energy used is used by buildings, whereas 50% of it, 25% used during the construction phase, and the remaining 25% are used during the occupancy phase. The major components causing CO2 emissions are the material used, the over-ordering, about 10% of material, and consequently waste. This has led to the buildings being a commodity-led property, a demand-led property, and constructed with shorter lifespan, with dominated by mechanical, electric, and electronic equipment. So, the built environment, we've all agreed that it has a lot of problems, and these problems have been well documented in literature. And in order to mitigate these problems, too many separate yet overlapping initiatives have been introduced. And this has led us to question the credibility of those initiatives. What is the construction industry supposed to be doing? Is it supposed to be following this initiative? And if it's not following it, is it neglecting the other one, or what? One of these initiatives is changing the perception of the building as a commodity and look into more sustainable features of the building, which determines the worth and the market of the property. And one of these initiatives is the initiative by the UK government to cut carbon emission by 80%, which is quite ambitious. That means that to use energy, renewable energy technologies with the different features, whether they're solar, wind, or biomass technologies, where biomass represent the major source for renewable energy. The microgeneration market in the UK is anticipated to be dominated by photovoltaics and and biomass combined heat and power CHP are expected to increase considerably. Okay, how do we perceive renewable or energy efficient buildings integrating renewable energy technologies in it? This has been well documented by Lewis Hellman back in the 80s, and to some extent it didn't really change a lot nowadays. So it depicts the developer as perceiving these buildings as funny. They take longer to build and are not cost effective, and in the end they will go wrong. The architect, since the developer will not pay for the extra work, so they're not bothered into integrating these because they're not going to get paid for it. As of the landlord, the rent won't rise because of using these technologies, and they pass on the electricity bills to the tenants, so they don't see themselves as involved. And the tenant, they don't want to waste their time saving peanuts on energy. And finally, the people in the work environment, they would perceive this building as oppressive because they have to take care of each and every element to save the energy. So it is anticipated that the inclusion of renewable energy technologies into the building from the outset would help make the buildings more energy efficient and acceptable by the users. It is estimated that inclusion of those technologies would increase the investment by 2%, whereas on the life cycle savings would reach to 20%, which is 10 times the initial investment. Great, so the problem now, we know where the problem is and we know the solution. Let's integrate these early on the building. But now we have two different examples, one that was built back in the 1800, and the other one was built in 2002. And both of them were rated as energy inefficient, although the new one was described by the architects as non-pollutant buildings. So we do have a problem, but what are these actually? This problem has been emphasized by the Minister Andrew Stanel, saying that there is a concern that energy efficient building or zero carbon buildings may become an empty slogan because of the industries failing to build according to the standards. But is it because of the industry doesn't want to follow the standards, or are there other problems? So in our paper, we've identified a number of barriers for the wider implementation of renewable energy, and these could be technological, geographical, economical, and in some cases, the suitable technology is not available in the market. And this has led to the concern that renewable energy technologies are bolted on the buildings, on the roof of the buildings, and causing damage to the building, and then the technology would be perceived by the users as unreliable, unfeasible to integrate in some cases, and with no consideration to space and aesthetic requirements, and therefore are believed to be installed to the detriment of profits. Another serious problem is the skills problem, and which is which the UK construction industry is suffering from. And integrating renewable energy to the buildings, there is difficulty in finding the proper skills for installers and maintenance personnel, and any other skills that may be required by the technology itself. So the causes for the underperformance of the renewable energy technologies could be that the design team being too optimistic about the behavior of the end users operating the systems. The computer simulations created idealistic controls, however, the actual performance varied, and the energy requirement was higher than that produced or predicted. The thermal bridging, although taken into consideration during the design phase, the actual construction does not necessarily follow the design. And most importantly, the commissioning, they don't look at the testing of the building as a whole after operation, rather the testing is done for the individual technologies. There is a serious challenge with regard to existing buildings, because they will be operational by 2050, but new buildings are still another challenge, and if we don't take these into consideration, we'll add to the problem of the existing stock. And therefore, the UK government has called for use of a modern method of construction to meet the market demand, which the government is constantly failing to meet. And therefore, off-site construction is perceived as being able to provide better quality, less waste, improve health and safety, and greater efficiency in the use of resources. Renewable energy technologies are more than just slapping on technologies on top of the roof. They're rather complex technologies that need to be integrated and require specialized skills. Therefore, the integration of off-site construction and renewable energy is claimed to allow alleviate the shortages in skills and the lack of proper commissioning. And by combining both energy efficiency because of the controlled working environment with the renewable energy technologies, we would have the chance to meet the target. Finally, there is a case presented in Japan where the building integrating off-site produced building, integrating renewable energy technologies was profitable, and because of they managed to they managed to benefit from the electricity bills cut in the building, and the mass production which also helped to decrease the cost of the building to provide renewable energy technology solar panels to the building as a standard rather than an option to the building. Finally, further research is required to actually prioritize the challenges that are facing the implementing and wider use of renewable energy to the market in order to help address these in due course. And looking into the difficulties of retrofitting those technologies into existing buildings, not to mention off-site produced buildings, because if they're not integrated with the buildings when they're produced off-site, this will cause other problems with regard to energy efficiency. In the end, I would like to thank you for your attention. I'm sorry about this automatic presentation. Thank you very much.
Thank you very much. I think the presentation was wonderful.
Thank you.
Some questions from the audience, please. Okay. I hope the audience has also noticed that if you want to ask some questions by text message, you can use the number provided in the message board. I have one question about the, you tell that the biggest problems are the technological and technical problems and also the maintenance. And I've noticed also in some projects that it's really, it's a great challenge implementing, for example, solar technology in cases where it has not been used before. So, do you think that there's enough training for this in the universities and schools?
I'm sorry, there isn't enough?
Is there enough training for renewable energy technology nowadays at universities?
Well, I think they're starting already to address these issues because there could be a trend that people, because of, you know, that's the trend of using renewable energy technologies and not looking into whether they're suitable or not for this particular case. This would result into them being inefficient. And now there is a lot of research taking place with this regard to avoid the problems that could happen later on.
Yeah, thank you very much.
Thank you.
The next presentations come from Germany. It's about an Energy Plus primary school in Hohen, Neuendorf. And the presentation is by Mr. Lütkemeyer. Please.
Good afternoon, ladies and gentlemen. I'd like to present a new built school building in Hohen Neuendorf. That is a small city next to Berlin. And we designed this building a couple of years ago. The building is finished this year and some of this year. The primary school in Hohen Neuendorf is the first new built plus energy school building in Germany. And based on the ambition of the city of Hohen Neuendorf to become a green city and the need to minimize the long-term running costs, the main objective for the design of the school building was to develop a sustainable concept that provides good learning and teaching conditions with low operational costs. Hohen Neuendorf is located north of Berlin. It's part of the metropolitan area of Berlin. The site is close to sport facilities, near to a kindergarten and residential areas. The building comprises of a construction of a primary school with an integrated triple-field sports hall. The primary school is designed for 540 children and has a gross floor area of 7,400 square meters. A central school avenue connects the two entrances with all functions of the building. Administration and teachers' rooms are located near the main entrance. The classrooms are grouped in 3 wings and are oriented to the south. Specialist rooms for arts, music, computing, nature sciences, a small library, and a cafeteria are oriented to the east. The sports hall offers a floor area of around 1,200 square meters and is divisible into 3 parts. The first floor is organized in the same way the teachers' rooms, the classrooms facing south, the specialist rooms, and the service rooms for the sports hall. An integrated design approach conceives all technical energy-based and functional requirements as an integral part of the architecture and permits a lean technical concept with a simple, easily controllable, and low-maintenance engineering system for reaching high-comfort indoor conditions regarding spatial quality, air quality, thermal and visual comfort. The Energy Plus concept was developed in close cooperation between architects and engineers, and the main technical features of the energy concept is the highly insulated passive house standard, a newly developed hybrid ventilation concept, an optimized daylighting concept, the use of renewable energy sources, and the integration of innovative building components. In cooperation with the teaching team, a room concept has been developed that enables different kinds of teaching situations, the so-called home area. The home area consists of a multifunctional room in combination with a smaller teaching room, an extended circulation space, a wardrobe, and a sanitary unit for each class. The technical concept for the ventilation and lighting is based on this room concept. By grouping the classroom and the sanitary unit to a home area in combination, a combination of natural and controlled ventilation can be realized. The advantages of both ventilation types are combined to a so-called hybrid ventilation concept to create a good balance of thermal comfort, air quality, user acceptance, and energy efficiency. The ventilation of the classrooms is primarily achieved by a rapid natural ventilation during the breaks using motor-controlled full-height vent windows. But with only this type of ventilation, the CO2 levels will increase quickly during the lessons. Thus, it is combined with a small mechanical ventilation for a slower increase of CO2 during the lessons. The supply air flow for the classrooms correlates to the amount of exhaust airflow needed for the sanitary units. The supply air is given to the classrooms. The extract air is taken from the sanitary units by using the circulation space as an overflow zone supported by air duct at the ceiling. A good thermal comfort in summer is achieved by means of passive night cooling using the motor-controlled vent windows, cooling down the large areas of thermal storage mass. One research objective in the project is the trade-off between thermal storage in the concrete ceilings on one side and a good room acoustic quality on the other side. To achieve best possible results for both requirements, the concrete ceilings are left uncovered for good thermal contact, and the biggest part of all available wall surfaces is covered by highly efficient broadband acoustic absorbers. Thus, a high room acoustic quality, according to the ambitious German DIN standards, can be achieved without affecting the passive cooling function of the ceilings. The south-oriented facades of the classrooms have been developed in detail to provide efficient solar shading, natural lighting, and passive solar energy gains. Fixed exterior blinds protect the windows against incident solar radiation in summer. Vertical fabric blinds enable efficient solar control due to the user's requirements. The windows above the fixed blinds have a nanogale glazing to diffuse daylight. The windows that are not equipped by external shading devices have integrated fixed solar shading and daylight guiding louvers. The external shading provides a shady atmosphere at the facade in summer, and a good view outside remains possible. So, the solar control and daylighting concept of the facade becomes an integral part of the architectural design. Almost every space is designed to have a high daylight autonomy. The circulation spaces are well oriented to the daylight to provide attractive room quality. The use of bright colors support the attractive appearance. The daylight performance of the sports hall was calculated also, and the design was improved to achieve good and homogeneous daylight levels. As well as the daylight of the public spaces, the room layout of the home area was developed for best possible daylight autonomy. The deep spaces of the classrooms receive natural light from two opposite sides. The small rooms get natural light from one side only. The building has a very good thermal insulation level that achieves the passive house standard. The U values of the opaque walls are between 0.11 and 0.15. The glazing is triple glazing with U values of 0.8. The main structure of the building comprises of concrete walls, concrete ceilings and a concrete roof for the school building and a timber roof construction for the sports hall. All the applied measures lead to a very low energy demand for the building. The calculated annual primary energy demand for heating, cooling and lighting is 23 kilowatt hours per square meter and year. A partial compensation of this need is realized by micro CHP, which is used throughout the year to cover the basic loads. For the compensation of the remaining primary energy demand, a building integrated photovoltaic solar power plant of 55 kilowatts is used. The annual primary energy production is 24 kilowatt hours per square meter and year. The design phase of the project was accompanied by a life cycle analysis. The planning team was supported in design, construction, quantity surveying and evaluation by a tool for integrated life cycle analysis called LEGP. The calculated operation costs for the school building are 70% less than the operation costs of a building of the same size and shape that refers to the German standards. The calculated life cycle costs are 25% less, and I think these are good news. The building was finished in August 2011. A 2-year intensive and 5-year long-term monitoring program started to evaluate the building's performance and acceptance. More information, you can find more information on these websites. And finally, I show you the team that was involved in this project, and thank you for your attention.
Thank you very much. Are there questions from the audience? I have one question concerning the natural ventilation during the teaching breaks. Do the windows open automatically, or do the teachers have to open them?
Well, the windows open automatically,
okay.
But the teachers have the possibility to open other windows by hand.
Okay, so they have to have fixed times for the classes?
Yeah.
Okay. Are there other questions? Okay, thank you very much.
Thank you.
Then we move on to our last presentations, which come from Japan, about the zero energy building project in the University of Tokyo. And please, Mr. Oka will present that.
Thank you. Not working? It should be working, but there could be some it should work. Okay, I tried. So, good afternoon, everybody. The original I am Ryozo Oka from the University of Tokyo. Original presenter of this presentation is Professor Yashiro, but he has urgent business at the present. unfortunately, he cannot attend this conference. Thus, I would like to make a presentation on behalf of him. The title of this presentation is very weak. Zero Energy Building Project in the University of Tokyo. And this project, this pilot project, have started about 2 years ago. And this is a definition of zero energy building in Japan. This definition is very similar with those of the other countries. So I'd like to skip this page. And this pilot project is supported by METI, the Ministry of Economy, Trade and Industry, Japan, and the New Energy and Industrial Technology Development Organization. And in this project, various experts committed in the process of design development. For example, architect, building service engineer, users, administrators, contractors, and researchers in the University of Tokyo, including me. So various design issues are mutually interdependent, and a regular basis meeting provides an opportunity for design integration. And this is the outline of this building. So 5 stories on the ground and 1 story underground. And this building is located in our campus in the Tokyo. And total floor area is about 4,500 square meters, not so large, a middle-sized building. And this is the inside of building. This building has convention hall and open space hall and cafeteria and several studio classrooms. And this slide shows the list of technology introduced here. These latest technologies 2 years ago. Later, I'd like to explain one by one. So at first, I'd like to explain the smart double skin cladding system with movable louvers. This is a section of louvers, and this is also a section of louvers. This is a movable louvers. And one surface painted as white, and the other side painted as black. And this louver can be turned over. So, for example, in the good season, this louver opened, and winter season, so black surface is outside, and white season is white surface outside. And there are many punching holes in these louvers. So even if louver is full closed, so we can see outside. So this is animation. I don't know whether this works or not. Sorry. This. Okay, it's work. It's work. Sorry, but stop. Sorry. So it doesn't work. So I'd like to skip this animation. I'm very sorry. So
I think they are trying to help you.
Just a moment. Okay. So I'd like to show you the situation, moving situation of these louvers. Okay. this is in winter, so black surface is outside. And this rubber can be turned over according to the outdoor air temperature, humidity, and solar radiation. And in summer season, this rubber, the surface, white surface, becomes outside. So thank you very much. And I'd like to move to next slide. Okay. In this building, ground source and water heat pump system is also introduced. So in Japan, in Japan, in Tokyo area, ground temperature is about 70 degrees Celsius. So we can use such ground heat directly for radiation cooling and heating panel. And also this heat is utilized for fan coil unit through heat pump systems. For the ground source heat pump systems, 100 meter 10 boreholes introduced, so capacity is 50 kilowatt. And the groundwater heat pump system is 2 multiplied 2 wells introduced, capacity is 70 kilowatt. So total capacity is 120 kilowatt. And this capacity is 1/3 of peak value of heat load of this building. And in this building, this slide shows the radiation cooling and heating panel systems. This is a ceiling set on the ceiling. Radiation panel can heat or cool a human body directly. This means this system is more efficient than the usual air conditioning systems. However, this panel cannot cover the peak load in the summer. In such a case, we utilize a combination of fan coil unit and radiation panel systems. And in this building also, desiccant dehumidifier is introduced as air handling unit. And exhaust heat from heat pump is utilized as recovery heat for desiccant rotor. And PV solar panel, the total power is 30 kilowatt. Peak power is 30 kilowatt is introduced. And the total electricity production is about 375 gigajoule per year in primary energy. And in order to achieve best combination of the previous devices, so integrated building operation system is required. And we have developed this system controlled by artificial intelligence. And this is a very, very brief example of integrated building operation systems. And traditional building, so control of lighting, and control of ventilating, and control of air conditioning, and control of so many other things are controlled independently. But in this system, such lighting, air conditioning, and opening lever is controlled simultaneously. And such operation is done by artificial intelligence. And this system employs a learning process. This is very similar with PDCA cycle. through this cycle, this system can find optimum operation solutions. And finally, I'd like to explain the roadmap for the achievement of net zero energy in this building. And this is a reference value, reference energy consumption. And this value is the average value of our university. 1,800 megajoule per square meter per year. This is primary energy consumption. And in this building, through the various devices, so energy consumption becomes half. This is at the present. And until 2030, through the reduction of optimum control and the reduction of improvement after replacement, and some assumption that PV performance improved 3 times. Through this improvement, this building will achieve net zero energy until 2030. That's all. Thank you very much.
Thank you very much. Are there questions concerning the presentation? Okay. Is everyone sleeping? Okay. No, that was a joke. It was really interesting presentation. You said that the energy use will you will reduce it 35% during the first 3 years in the operation. Yes. Okay, so the PV and the other things were installed after the building was ready?
Yes.
Okay, what was the reason for that? Why were they not installed immediately to the building?
Sorry, what's the reason?
Yes. Why did you install the PV system and the louvres afterward the building was finished?
PV. Okay, so in order to achieve zero energy, so we must produce energy.
Okay. I think I misunderstood it. Yes. Okay. Thank you very much. Okay.
Anything else?
That was the last presentation of our session, and I guess they have some coffee break now outside the room. Thank you very much for the listeners and the presenters.